So, hi everyone. It's our pleasure to welcome Henry Adams today. Henry is an associate professor of mathematics at Colorado State University, and he's currently on a sabbatical at the IST Austria. Henry is a prominent researcher in topological data analysis and related topics. He has applied topology to a number of problems and domains, including machine learning, computer vision, or quantum chemistry. Henry is also the executive director of the Applied Algebraic Topology Research Network, which is a remarkable effort towards community building around all aspects of topological data analysis. So today, Henry is going to share with us his perspective on the fruitful interactions between math and applications, with a specific example of persistent homology, persistent images. Sorry. So without further ado, Henry, the floor is yours.
Thanks so much, Julian, and thanks to the entire group and to all of you for being here. It's really a pleasure to be here in Paris. So my wife Elwo and I arrived yesterday morning and walked around, and we're really looking forward to our stay. So I'll be giving sort of a survey style talk. Some things that I was not expecting and learned over the years in terms of how persistent homology has been applied, things that I didn't predict, but after the fact, maybe we could have seen coming. So most of the work I'll be discussing is not mine. I'll be surveying lots of work by lots of people, but the main paper that I will be describing is joint with this team of folks who are currently or formerly at Colorado State University, and our persistence images paper was in the Journal of Machine Learning Research. So Julian mentioned AATRN. This is the Applied Algebraic Topology Research Network, and we're an online seminar that's been going on since 2014. But then when the pandemic hit, we decided to invest a lot of energy. So we have several different seminars. Between them all, we have about 1 or 2 live talks per week that you can join on Zoom. And on YouTube, we now are getting near 4,000 subscribers, which is pretty good for a field the size of applied topology, in about 24 hours watched per day. So we're always interested in ways to collaborate with folks. So if you have ideas or things you'd want to co-lead with us or suggestions, we're hoping to. So we have a form that we just created where folks can contribute videos. So maybe even without giving a talk, you want to share a video on our channel, you can contribute such a video. I think later this summer we'll be advertising a "This is my research" campaign. So targeted mostly at early career folks, but create a shorter video, describing what your main research problems are. This is a place where you can put this video on YouTube and it'll get seen. So folks have questions or would like to discuss online networking and academia, it's one of my interests. More research interests that I've worked on, but I won't be describing today, include Viator-Schrips complexes, how they relate to optimal transport, Gromov-Hausdorff distances, which are sort of the foundation behind shape matching in computer science, and Borsuk-Ulam theorems, which are a topic from topology. So I won't talk about this today, but there's a recent large joint project with groups from Ohio State, Colorado State, Carnegie Mellon, and Berlin, where we're relating Viator-Schrips complexes quite directly to Gromov-Hausdorff distances between spheres of different dimensions. Okay, so Gromov-Hausdorff distance is a way to associate a distance between 2 metric spaces. It's the motivation behind a lot of shape matching algorithms, but it's notoriously difficult to compute. People have started to find some preliminary information on, what's the distance between the circle and the 2-sphere, or the 2-sphere and the 3-sphere. And sort of through a surprising connection to Viator-Schrips complexes, we're sort of able to give a lot more information on entries in this table. But that's a story for another talk, but happy to discuss with folks during my stay if you're interested. So this talk, the title is a little bit of a pun, or I'm borrowing it from Eugene Wigner, who's a physicist. he has a paper titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." So why is it that mathematical models, that are often developed out of curiosity, why are they often so fruitful in modeling the real world? Right? Think of the theory of relativity, right? When Einstein needed this, the mathematics had already been invented and discovered, a century prior. So his article is sort of describing why he thinks the mathematical structure of physical theory points to improved theories and improved predictions. My talk will be the unreasonably effective interaction between pure and applied mathematics. Of course, you shouldn't necessarily try to divide pure and applied mathematics, but you have more theoretical ideas and applied ideas. And when you mix the two, you can often provide fruitful avenues for research, both in the applied or the theoretical direction. So why is it that when we apply mathematics to a problem, we motivate new pure math questions that we never thought of before? So I'll just give one case study, this project I've worked on for persistence images, which I'll describe. And I'll show how different theoretical or applied ideas were injected into the project at different times. And it really, pushed the project in new directions. So I have sort of two goals. First, to show machine learning applications of persistent homology in various areas. And then towards the end, I'll transition and I'll try to advertise the opportunity for further theoretical work, looking at how persistent homology measures not only global features, but also local features of a data set. Okay, so let me start from a high level. What is the difference between geometry and topology? Topology ignores some geometrical properties like exact distances or exact curvatures, but preserves others, okay? Sort of like instead of looking at the integer exactly, you look at the integer mod 2, and this can be valuable in some math proofs. So to a topologist, this coffee mug can be deformed to this solid torus, so they're the same shape. But to a geometer, these are quite different shapes. Amazingly, topology is computable, some parts of topology. So homology can be computed essentially using linear algebra and Gaussian elimination. So maybe there's a little bit less to store with topology. You just store the number of holes of each dimension, right? Whereas in geometry, you'd want to know all of these and choose two distances between endpoints. So some specific examples. This space has 6 connected components. So it's 0-dimensional homology, has rank 6. It has no higher dimensional holes, however. This picture here has a single connected component and 3 one-dimensional holes. A hollow sphere has a 2-dimensional hole. You could fill it with jelly and the jelly doesn't spill out. And a hollow torus also has a 2-dimensional hole. You could fill it with jelly and the jelly doesn't come out of your donut. It also has 2 one-dimensional holes, this loop going around this way and this loop going around this way. And any other loop you draw in the space is sort of a linear combination of those two. Homology on its own doesn't seem very useful, but it becomes more useful in this context of persistence. So let's track the holes in a space as the space is growing. So here I have a picture of a data set, and let's sort of blur our vision and add small edges and triangles and tetrahedron, and then sequentially add larger and larger edges, triangles, tetrahedra, simplices of all dimension. And we're sort of modeling our space at different scales, and maybe at some scales we recover the topology of the shape from which this data set was sampled. So maybe this data set was noisily sampled from an annulus, which we recover here. So in persistent homology, you're tracking the 0-dimensional connected components, the 1-dimensional holes as you go. So I have many 0-dimensional bars because I have many connected components. At this stage, things have connected up. So I have a single connected component, but no 1-dimensional loops. And then here I have a single connected component and two one-dimensional loops. That's why I intersect two bars. And then this large one-dimensional hole lasts for a while, whereas this smaller one-dimensional hole fills in pretty quickly. Okay, so sort of the range of scales over which a feature persists is measured by the length of the bar it produces. Any questions here?
Hello.
Okay,
So I have a question.
great.
What size is your penis?
So what I just showed you was persistent homology built on top of a data set. You usually add edges and triangles at an increasing level of scale. Another common setup for persistent homology is sublevel subpersistence. So here you just have a real valued function on a topological space. In this case, the topological space is just this square at the bottom, and the real valued function is the height of this volcano surface. Okay, so in sublevel subpersistence, you have a threshold, and you only include the points in the domain whose value under the function is underneath your current threshold. So we'll be raising the threshold and including more and more points from our domain as we do. All right. So at this low threshold, our region in the sublevel set is just a small crescent moon. And then we raise the height and we get this larger crescent moon. Keep going, finally this hole appears. We have a connected component that's new in the middle of this hole. And that connected component merges with what we had before. And then eventually the whole thing fills in. And so you track these features in the persistence barcode on the right. So when we first have a connected component, we get this zero-dimensional feature that lasts forever. Here we have our first one-dimensional hole that corresponds to this one-dimensional bar in blue. A new connected component corresponds to this short bar. It connects to what we had before pretty soon, so this bar ends. And then you can see when this hole fills in, that's when this bar ends as well. All right.
So is that how you know the
So a
penis
common
size?
representation for persistent homology is not only this barcode, but this equivalent representation of a persistence diagram. So let me show you how you change a barcode into a diagram. Let's do this for one-dimensional homology. Each bar has a birth time and a death time. So my first birth time is here and my first death time is here. And so I just recast this bar as a point in the plane whose coordinates are the birth time and the death time. Okay, and then my second bar, it has a birth time B2 and a death time D2, and I map that as this point in the plane. So you can almost take your bars and lie them vertically to get these points in the persistence diagram. All of these points are above the diagonal where birth is equal to death, just because the death time is always larger than the birth time. And we sort of interpreted a long bar as a significant feature in our data set, whereas a short bar we interpreted as maybe an artifact of sampling noise or something maybe less important. So in this persistence diagram representation, a long bar is just a point that's far away from the diagonal, and a short bar is just a point that's not so far away from the diagonal. So maybe importance is roughly stratified. Maybe you're getting less and less important as you're going towards the diagonal. All right. So persistent homology, I think one of its reasons for being useful in applications is that it measures not only topology, but also geometry. Okay. I mentioned how topology is being measured. We measure the number of holes at each scale, but you're also measuring geometry, the size of a hole or its persistence value. One paper that I like that reflects this perspective is not quite old, but it's one of the first papers that I know of where they really emphasize the point that small bars also matter in classification tasks. So they were looking at these data sets where you sample points from the brain artery tree. Okay, so here might be my brain, and we sample points from this brain. And then imagine, either growing balls around each data point, or what they actually did here is they looked at sublevel set sweeps of this data set of this tree of my brain. Okay, well, your arteries form a tree. So a tree sort of has no topology because you can contract it down. So we're not only just measuring topology, because here the topology is sort of trivial, it's a tree. This analysis is also measuring the knotedness and the curvedness of these arteries. So how are they twisted around in space? So their task was to distinguish young brains from old brains. A young brain from a 24-year-old has all this curvedness and knotedness and torsion twisting around. And then sadly, as I age, my brain decays away and I have less interesting geometry in my brain. So how this looked in their analysis is in the features. You just have in the young brain, you have many more features closer to the diagonal. Okay, measuring this local geometry of these small twists, these small cavities. And in the older brain, it becomes simpler and we have more white space comparatively near the diagonal. So this is not all that long ago, 2014, but a lot has been done since then. And a story that's emerging is that a lot of the value of persistent homology is what it measures near the diagonal. There's a lot of discriminative information near the diagonal. We sort of trained ourselves to think of points near the diagonal as noise and to disregard that. Right? And there's theoretical reasons, the stability of persistent homology, for disregarding points near the diagonal. So we trained ourselves to interpret persistence diagrams using the long bars and the points far away. But in machine learning algorithms, what the algorithm is often finding as the most discriminative is these points near the diagonal. Like an analogy you could make is that, a high persistence point is like a trumpet solo, right? It's very obvious. It's blasting out over the orchestra. But these low persistence points, it's almost like the violin section, right? No single violinist can you hear, maybe if they're out of tune, right? But together you can really hear the whole violin section quite loudly, and they send a clear signal. So this paper really pointed out that's the points of medium or short persistence that mattered for this discriminative task. All right, so let's start this ping-ponging of injecting new ideas from theoretical and applied directions. So we start with homology, which is quite pure. I don't know, it developed probably in the 1950s or so, counting the number of holes of each dimension in the space. Let's add in data, this applied perspective. We want to model the shape of a data set, okay? When you merge these two, one thing you might come up with is persistent homology, where you might recover the homology of a data set, right? When you increase the scale of the sampled points. A classic data set that I really like is this conformation space of the cyclooctane molecule. So here is an example cyclooctane molecule. It has 8 carbons in the shape of a ring, but the carbons can bend and stretch in different ways, okay? Each conformation of this molecule is represented as a point here in a 3D PCA embedding. So what do you see? You see a sphere with what looks to be a Klein bottle glue, or what looks to be an hourglass glued inside, but that hourglass is actually a Klein bottle, okay? So this Klein bottle is this 2-dimensional surface that doesn't fit in 4-dimensional space, but it doesn't fit in 3-dimensional space, but it does fit in 4-dimensional space. I mean, our molecule lives in 3D, but when you look at the conformation space of the molecule, you're in much higher dimensions, plenty of room for a Klein bottle to fit. So using persistent homology, you can recover the homology of the sphere with a Klein bottle glued in quite easily. Here's the 0, 1, and 2-dimensional homology of this space. So I've described this as a global analysis. We have this beautiful data set. Most data sets don't look like stratified spaces like this, okay? And we can recover the pure underlying homology groups of this data set quite easily. Another famous example where you're measuring global shape is this paper looking at image patches. So you go around with a digital camera and you take a lot of photographs of the world, and then you subsample down to 3x3 patches, okay? So each 3x3 patch, you can actually think of as a point in 9-dimensional space because you have 9 pixels, 9 grayscale values. They do some pre-processing which matters. So they throw away the patches that are all black, all white, all gray, and they look at only the high contrast patches where there's a fair bit of deviation going on. But what they find is, at different levels of density, you have first this primary circle of sort of linear gradients in all directions. These are the most common patches. And then at the next most common level of density, you have these 2 secondary circles that form that contain not only linear gradients, but quadratic gradients in sort of nature's preferred directions, the horizontal direction and the vertical direction. And then they sort of hypothesize that if you complete this picture a little further, you get a full Klein bottle. And in some sense, you can recover the homology groups of the Klein bottle from this data set. You can definitely recover the homology groups of this 3-circle model. But it's a global perspective. We're studying the shape of all of these image patches considered in union. Okay, so after persistent homology, folks started injecting machine learning into the picture. And so this problem arose of how do we vectorize persistent homology barcodes for use in machine learning? It seems like it would be easy to do, but I'll maybe hint why there's no canonical way to feed persistent homology barcodes into machine learning algorithms. So there's many, many ways to do this. Persistence landscapes is a famous one. Persistence images is what I'll describe here, but many groups of researchers were coming up with ideas essentially the same as persistence images at the same time. So about a half dozen research groups were doing this independently or while talking to each other, in the same period of several years. So how do you build a persistence image? You take your persistence diagram and sort of for convenience, we'll change coordinates where this depth axis will be replaced with persistence, which is just depth minus birth, okay? So this diagonal of 0 persistence now gets mapped to this horizontal axis, okay? So now high persistence points just live above the horizontal axis. But I still have this persistence diagram and new coordinates. What you do is sort of a kernel density estimation. You put a Gaussian over each point in the persistence diagram, okay? And then your persistence surface is the sum of those Gaussians. And then if you want, you can pixelize, turn the surface into a vector or first a matrix just by pixelizing and averaging over each pixel. And then whenever you have a matrix, you can just concatenate it into a vector. All right. So this is what we did for the first draft of persistence images. We had these persistence diagram points and we put Gaussians over this of the same height over each point. Okay. Yeah.
All these Gaussians, the height of the Gaussian was scaled by persistence. Right?
That's right. That'll be draft 2, I guess. Yeah. I joined this project late. So, I started at Colorado State in 2015. My collaborators already had posted, this paper on arXiv before I started working with them, really from the machine learning perspective. And then I sort of joined the project because we wanted to figure out how to make persistence images stable. So I'll sort of get into that in a moment. But already, even before I joined, they were realizing that they could do good prediction with these feature vectors. So you take something like this anisotropic Kuramoto-Shevchinski, dynamical system, and by eye, you can't really distinguish any of these 5 simulations. What was the parameter used to create these simulations? But for the machine learning algorithm, it's quite easy to identify the two examples that are chosen or simulated using a different parameter. Clearly, it's local features that are being used in this process, right? There's no global topology here. Another example that I liked is this linked twist map. So this is a discrete time dynamical system. You choose a random point in the square, really the flat torus, and then all of the subsequent points are deterministic from this first point, okay? And there's different parameters used, but no matter what random initial seed you use, with the same parameter, you get these similar pictures. I call this the ice cream cone parameter, because all the samples that you create from this parameter, you get this ice cream cone type shape, okay? So you might think this would be a good thing to use topology on because, you could measure the holes in this ice cream cone, right? And the topology probably is useful here, but I would hypothesize that the algorithm is using much less these holes and much more it's using these tiny little holes right here. This local geometry is probably what the algorithm is using more in its assessment. And you can test for that. Okay. This paper was not getting accepted anywhere it was submitted at first because of the point Julian raised. The pipeline wasn't stable. So you want to have processes and data analysis so that if you perturb your input just a little bit, then your output is perturbed just a little bit. Otherwise, what good is your algorithm in data science, right? You always have sampling noise. And if a little bit of sampling noise in your measurements changes your results, in an uncontrolled way, no one's going to want to use that. Persistent homology on its own is stable. So small changes to the data give small changes to the barcodes. Okay. But the first draft of persistence images wasn't stable because you can always have persistence diagram points that appear near the barcode. A really small change in your data, you can get these short persistence points. Take a smooth function and make it wiggly, and you get all these little points near the diagonal. So why weren't persistence images stable? Well, we had Gaussians of the same height above each point. So when a new point emerged near the diagonal, all of a sudden there's this Gaussian of height 1, right? Which changed our surface in a discontinuous way. So to make persistence images stable, we added in this weighting function, okay? So this weighting function is, typically it's a function of the persistence value. So this weighting function is usually just the persistence. So think of this as like a ramp that's 0 here, 1/3, 2/3, 1. It's increasing as you go up. So each Gaussian has height proportional to how far it is above, this horizontal axis of no persistence. And you can really see that here. We're weighting Gaussian points according to their vertical persistence value. We only have one point right here, and we get a really bright Gaussian, and we only have one point here, and we get a dimmer Gaussian. That's because these Gaussians have been weighted based on how far they are from the diagonal. Yeah.
If you want to keep the
No, the more questions during, the better.
I assume this weighting functions you optimize based on your specifications as well, or
Yeah, fantastic. We would have made much faster progress with Julian around. So at first we thought of this weighting function as a huge disadvantage. And in some ways it is, it's an extra parameter, right? What weighting function are you going to use? People use just the persistence or the persistence squared, or maybe the persistence, but then you threshold. So we thought of this as like, oh my goodness, our paper is never going to get accepted. But how it has evolved is that people learn the weighting function from the data. I'll show you an example of that. And people have done some really nice theoretical analyses. Theoretically, if you sample points from a manifold, what should be your weighting function to separate the signal from the noise? Yeah.
That relates to your observations about the school features.
Yeah, yeah. Well, fortunately, we wrote this paper in a general way where we say what's needed for the weighting function in order to have stability, right? So you do need the weighting function to be 0 here. Otherwise, it's not going to be stable, right? But to sort of pay attention to this local geometry, you're right. You want the weighting function to maybe, not increase too slowly, right? So you don't want to wash out necessarily all of these local features. So in this weighting function, I mean, we do wash out a fair bit of these local features, right? But there's actually a lot of signal here. Yeah. Other questions? Fortunately, our machine learning performance improved in many cases, or I think in all cases, when we added in this weighting function. I mean, you're adding in more parameters, so it's sort of cheating in a way. But another example that we did is we classified these very common shapes, point sampled from a unit cube or a circle or a sphere. And you sort of thought at first there was these high persistence points that distinguish the torus from the circle. But again, it's probably these small holes, like the sampling artifacts that have really been used in classification. Okay. Fortunately, the number of pure and applied questions then exploded. Folks have used persistence diagrams and persistence images in material science. So glasses have different shapes of how their atoms are arranged, sometimes crystalline, sometimes more in a liquid form. And you see these signatures in the persistence diagrams from different types of materials. Let me give you one nice example of how people use persistence images here and how you can sort of learn a nicer weighting function. So here are two classes of materials, the red material and the blue material. You sample persistence diagrams from both, and maybe you don't see any super obvious difference, okay? But then they transported these persistence diagrams into persistence images, and then they trained a linear regression model. So it's a very simple classifier, essentially hyperplane split in some persistence image space. And what they're able to use then, using persistence images, is go back and label which parts of the persistence diagram are discriminative for holes from the blue material or discriminative of holes from the red material. So you can look at a sample. This is a sample from the blue material class. And you can now go in using their nice algorithm and sort of say which features made the algorithm think this might be from the blue class, or which features made this algorithm think it might be from the red class, right? Overall, the algorithm has to give one guess or one confidence level, right? But you can sort of interpret why geometrically the algorithm made the prediction it did.
Is that the paper by Robinson Turner?
This is Obayashi, Hiroka, Kate Turner, and Vanessa Robinson.
I think they had something.
No. I think you're exactly right. You're seeing more and more. I mean, that's why machine learning is so good when you're in this linear space, right? You can sort of do more advanced things like this, like we know geometry is discriminative, right? But let's try to use geometry to make the algorithm more interpretable as well. Yeah. No, I think you're right. Robbins and Turner is another.
They had something along the lines of PCA analysis and organizations of persistence diagrams. I think the target was to do something.
I'll have to check that one out. But you can sort of like you can see how, so Yusu Wong and many others, they have a paper that does this directly, but you could see now how you might want to learn your weighting function to be discriminative for your task at hand, right? And this is something that's maybe not explicitly stated in this paper, but now has been explicitly explored in some others. There's sort of maybe a trade-off in some machine learning algorithms, right? Simple, but not very accurate, but easy to interpret. Folks definitely have looked at imputing persistent homology directly into deep learning, which is, state-of-the-art accuracy, but maybe harder to interpret. What I've thought about a little bit more is living in the simpler regime, so simpler machine learning algorithms, but you're trying to feed it more informative input. So topology or geometry inspired inputs is what you're trying to feed in, to sort of aid the interpretability. So it's sort of along the lines of feature engineering, trying to find the best features, which is not necessarily the most popular thing in machine learning right now, but I think it's a good way to add interpretability, find interpretable features. And persistent homology provides a pretty good out of the box way to sort of summarize geometry, summarize lots of global and local features, give it to a simple machine learning algorithm, see what it finds discriminative, and then you've learned something. What is the scale of geometry or topology that was useful? And then I can think more about what's going on at that scale in my data. Another example that I like, this is statistical physics, the Ising model. So you have sort of two states, plus or minus, and that state propagates, and it's sort of describing matter. In the simulation, you have a temperature, and you get simulated materials from a high temperature regime or a low temperature regime. So when you build persistence diagrams and then persistence images, you can see the authors have translated into birth persistence coordinates. You get things like this. And again, you can say what parts of the persistence diagram space were discriminative for materials from the high temperature regime versus the low temperature regime. And you have this interpretation that in the high temperature regime, you have bars that were born later or that die later. Whereas in the low temperature regime, what's more discriminative of that is very small bars, holes that were born early and die early. So Julian asked about this weighting function, should it be persistence or persistence that's truncated, or maybe persistence squared or persistence cubed? There's a really nice paper injecting theoretical ideas here. So this is Vincent Deville, who some of you might know, and Wolfgang Polenik. So they studied this problem of sample points from a manifold of dimension n, and then sample more and more points. You're always going to have noise, right, in your persistence diagram. And in the limit, as you sample more and more points, as a statistician, you want to be able to prove that you can separate the signal from the noise. You can separate the two one-dimensional holes in this torus from the noisy holes. Okay, so we're looking at one-dimensional persistent homology. These different rows are different weighting functions. The weighting functions were just the persistence or the persistence, just the persistence or the persistence squared or the persistence to the 100th power. So different polynomial functions of the persistence. And they prove what your weighting function should be, what the degree of your weighting function should be in order to separate the signal from the noise in the limit. So I think your weighting function, the degree of this polynomial, should be at least the dimension of the manifold. Okay. This is a very different weighting function than what people are using in machine learning applications. In machine learning applications, you have something linear where the weighting function goes off and then truncates. But they're looking at things that are like, polynomials raised to high degree, here raised to the quadratic degree, because our torus is of dimension 2. Right? And so if your weighting function has degree correct, you separate the signal from the noise. Whereas if it's too low, the noise dominates, okay? And if your weighting function has degree that's too high, yeah, you have the signal still, but the signal might get blurred together. These two one-dimensional holes might get combined. Somewhat.
Do you have an interpretation of the explanation of this result? Why the degree of fundamental related to the explanation?
That's a really good question. We should ask Vincent and Wolfgang, but here's my first explanation. So sample points uniformly at random in unit cubes of different dimensions. There's no topology, right? There's only noise. But in the unit 3D cube, you're gonna have a lot more noise than in the unit interval, right? So so when you raise this weighting function to higher degrees, it's sort of like you're emphasizing the more persistent points and de-emphasizing the, right? So if in a cube you have a lot more noise than you do just on the interval, right? You probably need to weight that to a higher power to dampen out the extra noise. Yeah, so I think you have more and more noise in high dimensions, and so you need a higher degree thing to dampen.
That's related to the person.
So just to be sure I understand, because what I learned was from Julian's talk about persistence diagrams, so I'm not an expert, but what I learned from Julian is that they used to from optimal transport to compare persistence diagram. And now you say you want to do something else.
Sure.
You explain, I mean, what would be the advantage of doing what you propose as opposed to using like optimal transport distance?
Yeah. So optimal transport distance can be used to define like Wasserstein distances between persistence diagrams, right? And I mean, it's the right perspective. It's the right metric on persistence diagrams. And I've used optimal transport a lot in some topology work I do. What you do when you interpret persistence diagrams in this Wasserstein space is from a set of persistence diagrams, you get a distance matrix, right? Maybe you have 100 persistence diagrams, and now I have 100 choose two distances between them, right? In machine learning, you certainly want to be able to do be able to do more statistical things like means and averages, but also sometimes linear things. So statistical things like taking averages in Wasserstein space, I mean, you can do, and it's very valuable and has been used on persistence diagrams. This is persistence images and persistence landscapes are going one step further. They're really embedding you into Euclidean space or sort of like a Hilbert space where you have an inner product, where you have more machine learning tools at your disposal.
Also embed Wasserstein space in Euclidean space. So why your embedding is supposed to be better than embedding using various tools from optimal transport?
No, I mean, this definitely not supposed.
I understand the point, but for me the point is like Wasserstein is non-linear, so it's difficult, and you use like linear method because it's simpler.
Yeah.
The points you're making,
No, I mean, I agree with you, and right. So you're proposing why not look at Wasserstein distances, and then you have this metric space in Wasserstein space and embed it, into some linear space. I mean, people are doing this, and it's super valuable. I would say there's sort of a zoo of different approaches: persistence landscapes, persistence images, Wasserstein approaches, sliced Wasserstein approaches, and I was at first. I mean, I'm saying this, which might go on YouTube. So I'm saying this, I was at first not very optimistic about this paper. I did not expect this paper to do well. And I didn't, I predicted wrong how well this paper would do. So I was like, okay, let's make this algorithm stable. And then I want to move on to other things. Now, this is by far my most cited paper, right? And so this was a case where maybe we didn't have the computational tools at that point in our subcommunity to do computations quickly in Wasserstein space. I don't know. So these different perspectives, landscapes, images, Wasserstein perspectives, and others, many of these papers have been, used and played off each other quite a bit. So I took very much your approach at first. This is, there's no reason you should put a Gaussian around each point, right? It's not the right kernel density estimator, it's sort of like ad hoc, a little bit black box. So I was quite surprised, right, when this sort of ad hoc perspective led to real theoretical analyses, right, that are more, my bread and butter, which I value. So no, I think you're right. I think your proposing is definitely extremely valuable perspective.
For instance, is it possible to do similar stability theorems using this type of distance as opposed to Wasserstein distance?
Definitely, yeah. I think you certainly still have stability, like and in fact, that's sort of how you phrase stability, right? If you perturb your input data just a little bit, then the persistence diagram changes only a little bit. And so the first metric people used on persistence diagrams was this bottleneck distance, which is like L infinity Wasserstein, but it's better to use, like LP Wasserstein. Yeah.
My understanding is that basically those vectorizations were already somehow to be used by people in the global machine learning community. It was more accessible. And so there was the stability properties that go with most of them, such that you can still have some warranties.
Actually, so always the same dichotomy between Wasserstein and NMD, because this is like kernel estimation, so it's like NMD norms. And machine learning, they have also the same discussion, but it's not clear if anyone has proved some superiority terms. I mean, in MMD, they would say
What's MMD?
maximum is kernel method. What you do is
Oh, yeah.
you compare them using a kernel method.
Yeah.
So this was they called MMD, maximum mean discrepancies
Mm-hmm.
in statistics, which is a given space. And then, but they never come with like a theorem or some clear explanation of why MMD is better, except the fact that in high dimension, MMD is better. So it's one thing I would like to understand better if there is a case study.
Yeah.
I could say.
Too often in my too often in my opinion, these methods are being compared based on machine learning performance, right? Persistence images have done quite well in terms of machine learning performance. I think that's partly why they've been used. But I agree with you. It's like these theoretical guarantees are what we need to do.
If you say experimentally it was better, for me it's a perfectly fine. It's probably the best answer.
Yeah.
I don't know.
Maybe Gabriel is coming with his own questions regarding optimal transport and MMDs. But yeah, I'm not familiar with the usage in machine learning. In our community, we try to use that for visualization, and we have some application motivations to keep the original signatures so that we can go back to the data and look at the individual features.
Mhm.
My understanding is that this is something that is more difficult to achieve. Transition like that.
I see.
This is why we're at least in our group, we're not looking very closely at the missing transitions.
Constructing a shape from its signature
Or given such a vectorization, if you have high persistence features, for instance, being able to cover in the original data what is the cycle that corresponds to highly permanent thing. When you have one signature, the interest might not be obvious, but when you're trying to interpolate things or when you're looking at various signatures, you want to see how the different features in the data sets are related to various signatures. I mean, with a signature like that, I would not know how to do it with confidence, but maybe this is
persistence landscapes are worth considering because when you average persistence landscapes, you don't necessarily get a landscape back. But if you just have a single persistence landscape, that determines the barcode exactly. So that's fully invertible, which is nice. So let me wrap up quickly just to give a brief perspective on local geometry. So in applications, what the algorithm is using to make its prediction is often much more local instead of global. I just want to mention a couple of papers that have looked at this theoretically. I think there's a lot more room to look at the theoretical way you can say that persistent homology is measuring local information. So one paper is coming out of this group at Florida, I believe, where they show that you can use persistent homology to detect local curvature. So sample points from a disk that's either flat or negatively curved or positively curved. There's no topology, but you can look at the short persistence diagram bars to tell if you're positive, negatively, or zero curved. And we looked at this project using persistent homology to detect fractal dimension. So sample points at random from a fractal shape like a Cantor set or a Sierpinski triangle. Well, you can use the short bars to detect the fractal dimension. And Benjamin Schweinhardt and others have really taken our work and proven some nice things about it. In dimension 0, what you're doing is you're sampling more and more points, and then you're building the minimum spanning tree. And you're looking at how the edge lengths of the minimal spanning tree vary as you sample more and more points, right? So sort of to what power do you need to raise the lengths of all the edges in the minimal spanning tree so that as you sample more and more points, this converges to a bounded number. But then if you look at higher dimensional homology, you're looking at lengths of one-dimensional loops or two-dimensional voids in this fractal measure instead. All right, so let me end there. So thanks very much for your time and questions.
Well, thank you very much. I guess we should any questions in the audience as well as the online audience. If you have questions online, please don't hesitate to type them in the chat window and I will pass them on. Do we have questions?
Yes, we have a question. Can you go back to the slide where we have a feature of contents for the red class and the blue class?
Yeah, this material.
So what is the figure A and B represent which persistence image?
Right. So this is sort of, okay, so they're doing sort of a linear regression, but think it's sort of like a support vector machine. So they're finding a linear separator, you know, between the two classes. Okay. This is sort of the you know, this is what the separator looks like in high dimensional space. So, you know, it's sort of like it's telling you the direction you move to go towards one side of the separator or the other. So if you want to move in the direction of this red material, you know, add more persistence diagram points here in this red region. If you want to go closer in the direction of this blue material, add more persistence diagram points here. So this is the sort of the direction of the separating hyperplane in high dimensional space, where blue is the features discriminative for this material and red. Okay, and so this is where you know, each pixel is weighted based on how important it is for the blue or the red class. And then this has just been thresholded. Yeah. Yeah. So it's not a persistence image itself. It's sort of showing you a direction in the space of persistent images. It's this discriminative direction. Yeah. Yeah.
We have one question for this. So, yeah, very familiar with this persistent dimension. You mentioned stability. Can you quantify the stability?
Yeah.
Is there a kind of measure?
Oh, definitely. Yeah, completely. So let me give myself a little room to write. All right. So I'll just sort of write down the statement and then describe it a little bit. All right. So, all right. So X is some metric space, right? And so Y is some nearby metric space. You said you're familiar with Gromov-Hausdorff distance? Okay. Yeah. So that's just some notion of distance between metric spaces. Okay. Here. And then here, what we're doing is we're building the persistence barcodes on top of these two metric spaces. You know, here's, you know, an image of how we're building the persistence barcode, I don't know, on top of Y. Okay. This bottleneck distance, it's, there's two ways you could think of it. And maybe I'll, okay. So here I have persistent homology for Y. And then in blue, I have the persistent homology for X. Okay. This bottleneck distance you should think of as an L infinity type Wasserstein distance. Okay, so you're looking for the best matching between this blue persistence diagram and this red persistence diagram. Okay, and the bottleneck distance is looking at the length of the longest edge. Okay, but there are also versions of this using Wasserstein distance here, right, where you're looking at an LP weighting of all of the edge lengths in this matching. So this is sort of the, you know, one of the metrics on the space of persistence diagrams.
It does a good understanding of what, I guess it's impossible to have a reverse inequality, but it has a good understanding of shapes that will be poorly controlled using the consistent diagram.
People have looked at this. I mean, it's a pretty restricted class of shapes. You know, if you look at, you know, trees or, you know, I think, what are they called? There's a particular class of metric spaces that essentially describes all trees and nothing else. You know, they're metric spaces with a max type metric. They satisfy not only the triangle inequality, but the triangle inequality with a maximum. So those spaces are fully described.
You mean for these spaces, the inverse inequality is really not true?
For these very simple spaces, trees, you get either an equality or you get a Lipschitz bound on the other side.
Okay, but I would mean rather the opposite, that shape where this opposite bound will clearly never hold.
Oh, yeah,
When
no.
you say that using these tools, it should not be used.
Yeah, no, so yeah, let's put down an example where it's clear that this is not going to be tight or near tight, right? And so you should think of this as a signature, right? It's measuring some information about the Gromov-Hausdorff distance, but certainly not all. I mean, this is sort of NP, Gromov-Hausdorff distances are NP hard to compute in general. So you can get polynomial computable lower bounds, right? Yeah. So, I mean, just do the following. So, look at a torus, versus two circles with a sphere. Okay, so sample each of these spaces really, really finely, right? And then sort of arrange the geometry. They have the same homology, two one-dimensional holes and a single two-dimensional hole. Do some work so that you arrange the geometry so that the bars have the same length, as well. Okay, and then yeah, you can get these barcodes as close as you want by sampling more and more points and, prescribing the exact lengths correctly. Right? You can get the bars as close as you want, but the Gromov-Hausdorff distance is. Yeah.
If the left-hand side is small, and the activation of the consistent diagram, so also the Gromov-Hausdorff distance is small.
Right. I mean, I'm saying you could take an example like this and you could show that you can make the distance here arbitrarily small, but the distance here, above 1.
So
Yeah.
then how can you put the
Oh, so this is showing that you typically can't prove things of this form.
My question wasn't about stability, was opposite. If you have one very small and the other one very large.
Yeah. So you typically can't.
The reverse direction.
You typically can't reverse this.
Okay.
Yeah. But I think.
Say Gromov-Hausdorff is much stronger than the
But there's a lot of work to be done here because I sort of gave this example and I waved my hands and I sort of convinced you that something like this should be possible. Okay, but a lot of my theoretical research is when you take a simple shape like a sphere or a circle and you build a Rips complex, what is the persistent homology that you get? And so when you build a Rips complex on top of the circle, you recover this homology of the circle for a while, but then you get a 3-sphere and a 5-sphere and a 7-sphere, so like if you're allowed to use higher homology, these won't have the same barcode. So there's more to this story. And I think it would be valuable if somebody, really took an example like this and
is there some understanding if you go to higher homology that you can somehow build, of course, this would not be polynomial anymore, but things that would somehow converge to
potentially, yeah. That could, something like that. I mean, something like that is more likely to be true. People have done work where you look at local persistent homology. So you don't just look at one persistence barcode, but you look at all these local patches and you look at persistent homology on each local patch as well. And that might be closer to having reverse inequalities. I mean, even this example, you could look at the cup product cohomology to distinguish these spaces. So people look at cup products. So, I mean, it's a what you're proposing, trying to look at bounds in the reverse direction, people are doing, but it's hard. Please.
So in the last almost you mentioned about this rate function. Said that they separate signal to noise in the beginning, right?
Yeah.
So can you explain what exactly?
Yeah. So where was this? Here we go. Yeah, so this is his Devol-Polinick paper. So, and the limit, I mean, sort of is, n sample points. You're taking n to infinity. With, you have a torus and you sample 100 points, then 1,000, then 1,000,000, then 1 billion, right? You always have sort of both persistence diagram points that correspond to the homology of the underlying torus. And you always have points that correspond to just like sampling artifacts, as you're filling things in, right? So there's both signal and noise. But in the limit, as you take n to infinity, which is dominating, which is swamping out the other. So like which part of the persistence diagram is the magnitude going to 0, versus the other one going to 1, if you sort of scale this surface to have volume 1 underneath it. So
Can you quantify the distance then? So, wait, is the distance, yeah, how many people confused will be between distinguish the two?
yeah, so we're,
You impose a metric and then you say that.
yeah, so I won't give you the exact metric because it's not my paper, but let me, yeah. So we're sampling these points, building these persistence diagrams, and then we're putting a Gaussian over each persistence diagram point. And each Gaussian has a height, which is how far away it is from the diagonal, right? So that's this power here, okay? So we produce all these persistent surfaces, these sums of Gaussians, okay? Let's normalize each persistent surface to have volume 1 underneath the curve, okay? And so part of that volume is going to be coming from the signal part of the Gaussians, and part of that volume is going to be coming from the noise part, okay? So in the limit, as you sample more and more points, if you choose your weighting function appropriately, then in the limit, that volume is under the signal part, okay? And if you choose your weighting function as a polynomial of too low degree, then that volume is under the noisy part. So the signal gets swamped by the noise, right? This part of the surface, yeah, there's a little bump here because I had a couple persistence diagram points, but they're not weighted high enough. So this part of the surface in the limit, it's sort of like it gets ignored, right? So you might as well not have been sampling from a torus. You might have just been sampling from a square. You see what I'm saying, right? But if you have your weighting function appropriately, the signal is sort of maintained. So I think this is a really nice perspective, in my opinion. I mean, I'm a mathematician. This is a statistician perspective, but I like this perspective.
Does this property holds when you generate persistence diagrams of scalar functions?
Like great question. Yeah. It's a really good question. They don't look at that, right? They just look at this Viator strips or check persistence. So there's a paper that came out of WinCompTop. I know Teresa Heiss is one of the authors, and I think maybe Brittany Story, where they look at sublevels of persistence and the sort of noise that you get when you discretize, when you pixelize, right? And other people have looked at this, but there should be a similar analysis that could be done in that context, right? I mean, going out of persistence images, what would be the weighting function? So I think that's a really good question, and I haven't seen anybody look at that before, so I'd be interested in that. But you could also have noise like add L infinity, add small little perturbations, that you have a model for taking your function and adding some noise to it. I think that might be even better than the
noise assumption of the sampling of the.
Yeah, I mean, but this must be similar in spirit to things your group works on, right? That's a good question.
Yeah, I have a question.
Yeah.
About the weight function.
Yeah.
Not really, but more about the resistance ranges.
Yeah.
Is there a way for you to know if you learn more from the resistance and the width? Because you have the two information in the image, right?
Mm-hmm.
So I guess another question would be like, why would you use only the resistance to optimize the function? Because you have different information.
Yeah. No, I mean, we allow the weighting function to be any sort of, continuous enough function on the plane. So long as it's 0 along the diagonal, I suppose. So So yeah, the most common weighting functions are only functions of the persistence, right? But no, you're right. It could be whatever function you want over the plane. You know, you want it to be 0 here, you know, but it could, you know, it could be getting larger, you know, in all those directions. That's really fine. That's not what's most commonly used, but that's really fine. Yeah.
We have other questions?
Yeah. I mean, I could, we, mhm. Oh, no, yeah, we only have one direction. Yeah. So yeah, it's in the, yeah. No, this is a context where we give bounds of this form, right? Where we sort of have constants here, or we have, you know, some constants here that depend on the parameters used in your persistence image. But this reverse inequality is really impossible in that level of generality. There's no hope, just because you could have two very different data sets that have persistence images that look as close as you want. Right? Yeah.
I may have one last question, and I'm sorry if it looks unrelated.
No.
Some of your explanations, but it's a question that I ask every time to people in topology.
Oh.
You have their feel, and so basically I'm going to ask you the question that will feed my survey.
Okay.
So basically, homology in low dimensions is well understood, and you showed at the beginning of the talk a lot of illustrations that connected components, cycles, and voids. And I wonder if you came across application example where homology in higher dimensions was really important.
Great question.
The only one that comes to my mind is problems of inference regarding intrinsic dimensions. Manifolds where they were trying to guess what is the intrinsic dimension of a very high dimensional space by looking at the different persistence diagrams. And I wonder if you came across other.
And when is that paper from, or who's it by?
I don't recall. I'm sorry. I think it's a paper in physics.
Yeah, great question. So yeah, I agree with you. I mean, the vast majority of the applied papers are looking at 0-dimensional persistence, 1-dimensional persistence, definitely 2-dimensional persistence, void, you know, in 3D materials.
That would be the first one to do it because we're mostly interested in imaging data, so low dimensions, but still I'm interested about if you ever done it.
Right. In terms of applications, no. I mean, I think dimensions 3 and higher, I haven't really seen in applications. It's something, you know, I'm quite interested in the theory of persistence in all dimensions. You know, when you build like a Viator-Schrips complex on a very simple space, like a sphere, you know, we understand what happens for the circle, but even for an n-sphere, we don't understand what happens. So I'm looking at these questions from the theoretical perspective, but I'd be very interested in more applications to advertise this, because I mean, you can get 3-dimensional homology when you build a Rips complex on top of the circle, right? So this is sort of a warning. Just because you see high-dimensional homology in your data, don't think that you really have some 3-sphere or something in your data. Yeah. And another word of warning here is that, I mean, on data sets, over many years, people will see some very short, like 7-dimensional homology if they're able to compute that far, right? And they'll ask, like, where's the 7-dimensional hole? And the answer is almost always no. It's some like low-dimensional geometry that, because of the way you're constructing this filtration, builds a 7-dimensional. I mean, from the mathematical perspective, right, materials are just sort of like random samples of points from different distributions. So I think it's very interesting mathematically to study higher dimensional materials, like materials in 4D, materials in 5D. So there, material in 4D, you will have 3D voids, right? I mean, I've looked at evasion problems before where you have like, along the lines of Geist and De Silva, you have sensors and you're trying to study the covered region, or you have mobile sensors and you're trying to track evasion paths. And similarly there, it's most applicable in 2D or 3D, where you actually want to sense an environment. But mathematically, you can ask, how does this work if I want to monitor a 4D or a 5D environment, right? So you would use higher dimensional homology there. Well, okay, so let me say this. So yeah, I like the answer you gave.
This is a discussion we can have afterwards. Henry is here for 2 days, so if you have other questions as well, please don't hesitate to reach out. All right, so I guess we can thank the speaker again. Thank you.
Thanks so much.
I will stop